So I'll show you some sketches of how we work on that. Mario already explained that a little bit to you. I've got another method here called micro-lensing. Now once in a while, if you look in the right direction, say towards the middle of our galaxy, there are so many stars in your line of sight that one will cross in front of another, almost. When this happens, the one in the middle can bend the light of the more distant star enough to magnify the image of the distant star, and what we see is that a distant star will gradually, over the course of a year or so, get brighter and then fainter. Now it turns out, if you're very, very lucky, and there's a planet around this little star, it'll make its own little blip on the curve. And so this has been now done for 7 different star systems, and one of them happens to have 2 planets that can be seen this way. So it's a very complementary technique, and this has all been done from the ground. It can be done even better in space, and maybe we'll do that one of these days. So we're beginning to learn. Now most recently we've been beginning to make direct images, and Mario showed you at least one picture of those. And finally, timing. We have a few planets that have been discovered orbiting pulsars, which is not exactly where you go living, because a pulsar is a very nasty source of immensely intense radiation. But it seems when a star system completes its life and turns into neutron stars and pulsars, that once in a while either planets are formed from the debris, or they were still there from left over from beforehand. So we're able to do this most amazing thing. Now, this year we have recently launched the Kepler mission. This is an observatory built specifically to follow to discover planets like Earth orbiting stars like the Sun. And it is up there. It was just launched a few months ago. It is to be pointed at the Cygnus region of our galaxy, where it has the possibility of seeing the most possible stars at one time. So they will be monitoring about 100,000 stars continuously for several years. And the purpose of this is to see some of them blink. So the calculations say they should discover a handful of planets like Earth around stars like the Sun, if they're at all interested at all. And of course, thousands of other easier targets are likely to be found as well. So we will see what they see, but the expectation is this will be the first measurement of how abundant are planets like Earth around stars like the Sun. It'll take them a while, because obviously if you see one blink, you don't know what happened. You have to wait for another year, if it's an Earth around the Sun, for the alignment to reoccur. So you have to watch this many times and be very, very confident. But I think that over the next few years, we hope to hear from them that there are many places like home over there. Now, how much like home, that remains to be figured out. We need more measurements. So we've got an illustration coming here about how the planet can obscure light from the star. And you see the graph suggesting that the star will get a little fainter as the planet goes in front of it. Mario showed you something equivalent to this. In the right-hand picture, we've got a similar story, except when the planet goes behind the star, something also may happen. If the planet is bright enough, you will also notice that the total light of the system is diminished when the star blocks the light of the planet. So this has been done already with the Spitzer Space Telescope, which has been in operation for quite a few years now. This only works when the star is pretty faint and the planet is pretty bright, but nevertheless it has been done and does work. So more of these detections are likely to happen. So what can you learn from these kinds of things? Well, as Mario pointed out, some of the light from the star will go through the atmosphere of the planet on its way to your telescope. So if that then will enable you to study the characteristics of the constituents of that planetary atmosphere. Also, once in a while, there's a possibility with enough sensitivity, you could even detect the effect of a moon around a planet if you could do this. And if you're very lucky, maybe you'll even be able to tell if the planet has water in its atmosphere, depending on temperature and many other things. So, in the very long term, we have many hopes for this technique. It's the first technique that's been effective to learn details about the atmospheres of planets. So we have, just to illustrate another way of going at things, quite often a system like the Sun, with its planetary system and its interplanetary dust, will be visible from a distance because of the dust. So here is a close-by star called Fomalhaut in the southern sky. We saw with the Hubble telescope, and Mario showed you the picture, that there's a ring of dust orbiting around that star. And even a long time ago, it was recognized this ring of dust is not where it's supposed to be. Number one, why will dust be in a ring? And number two, why is it that it's not orbiting why is the ring on a star? And so the upshot is we figured the planet had to be there. So since then, we've also got some more pictures taken from the ground. If you make a very good telescope on the ground and you can correct a bit for the fluctuations of the atmosphere with adaptive optics, then you can take pictures of stars from the ground and hope to see planets. So the one in the upper right there is done with the with the Gemini and the Keck telescopes and adaptive optics. So there's three little things labeled up there, A, B, and C, that are planets moving, and we've actually been able to wait long enough to see them move. The purple and red thing in the middle is actually not the star, but the leftovers from the optics that said, well, okay, that's the best we can do. That's what the star looks like through our imperfect optics in the atmosphere of the Earth. So what are we going to do next? Well, clearly, Europa is an interesting place in our own solar system. We've heard a lot about how Mars is not the only wet place. Besides the Earth and Mars, there are 4 wet places that are known in the solar system. This is one of them. It was discovered by Galileo. And Ganymede is similar. Both of these have oceans covered with ice. You can see that Europa has this amazing structure that looks like ice flows with sort of muddy water coming up between the cracks. I think we have recognized for a long time, since this picture, which was taken by the Galileo mission, by the way, that this is a wonderful place to go studying and thinking about how water works in the solar system and to see if that material has any signs of organic chemistry in it. Now, it's pretty dang hard to drill through this ice down to get to some real water underneath. People have drawn pictures of nuclear reactors melting their way through, and so it's going to be kind of hard to learn really if there's pond scum under the surface, but you know it could be. And then also in the system around Saturn, we have two places that are alive. You've probably heard about Enceladus, which has these little spritzers of volcanic water coming out. And we flew our probe through the spritzers, through the plume to measure them. It's also been recognized that Titan, where we landed a probe and got pictures, has a surface that's completely made out of ice with lakes of methane and ethane surface. The surface of that little satellite, big satellite, has been shifting. So we figured, well, okay, how can the surface be shifting? Well, it's floating on something. The calculation says, okay, the surface of Titan is made of ice and it's floating on liquid water underneath. So we've got 4 places in the solar system besides Mars that are wet. Alive, that's another question, but they're wet. So what else can we learn about our own solar system? Well, we now have 8 planets in the solar system, but actually there are hundreds and hundreds of things out there in the distant part of the solar system to study. So Pluto got demoted because he was about to be outclassed. So we have here a drawing that says this is what the known ones look like outside the sort of way out into the outer solar system. You see this has already one that's bigger than Pluto. The one that's marked Eris there has a curve around it, and so does Makemake. I think both of those are marked that way because they have the possibility of having at least a temporary atmosphere when they get close enough to the sun. So you see some of them also have their own little satellites with them. That's a very remarkable find those rocks, see what they're made of, and learn what you can about their orbits, and figure out when they could have, or if they did come towards Earth, to give us some water and some carbon. So where are these objects? This is an orbit diagram that shows you where they are. The horizontal axis is distance from the sun. Vertical axis is the inclination of the orbits. So you see most of the orbits are not exactly 0 inclined.